Jnanam paramam dheyam. Knowledge is supreme.
Today now what I will confine is to prove this triangle inequality, which you are familiar in linear vector space language, and Cauchy-Schwarz inequality. So what is Cauchy-Schwarz inequality and the triangle inequality in this language? So if you take a norm of psi plus phi, you can write a triangle. You can call one vector as norm of psi and norm of phi. That's the length of this side of a triangle. Then what will this be? If this is a psi vector and this is a phi vector, you need to take psi plus phi and then take the norm. Is that correct? Yes, everybody is getting used to the notation. If I write A vector, B vector, all of you will be familiar, right? If suppose I call this as mod of A vector, this as mod of B vector, if I call this as mod of C vector, which is nothing but mod of A plus B vector. What is the triangle inequality? Mod of C should be less than or equal to mod of A plus mod of B. I am just mapping it. Whatever I have written here is also true for an abstract notation in any dimensional vector space. Could be complex or real vector space, it does not really matter. But this property will be satisfied. What is the property? If I take psi plus phi and then take the norm of it, that should be less than or equal to the state psi norm of it plus state phi norm of it, right? This is what we call it as a triangle inequality. So I want you to try and prove this, where you know how to write this norm as an inner product, and you have to use the property that psi phi is phi psi star, right? We have these properties that psi phi is phi psi star. And then you need to prove this. Discuss these proofs at some point, either in the tutorial or in the session. But before we do it, get used to this Dirac bracket notation and try and prove the triangle inequality. So the next one is A dot B is formally you would have written it as norm A, norm B, cos theta. So A dot B is generally less than the magnitude, will be less than norm A, norm B, because cos theta, what is the values of cos theta? The range is from -1 to +1. So if you take the positive magnitude, then the left hand side should be less than or equal to. But the same thing for the inner product, we need to replace the dot product by an inner product for an abstract vector which defines a quantum mechanical system and prove this property. Okay. How do I write this? I could write this A dot B, as I said, you would have written it as phi psi, but then I will take mod squared, that is invariant under psi phi interchange, right. Phi psi inner product is psi phi star, but mod squared of psi phi is the same, and this will be less than or equal to phi phi, which is the mod squared of it. So, I am just squaring both sides, okay, what I am doing. What else? It's not right. Psi psi, is that right? So, maybe let me write it again. It is phi phi times psi psi. So, this is the Cauchy-Schwarz inequality. When will it become equal? If psi is 8 times phi, then equality holds, right. What is this condition? If psi is some linear multiple of phi, then psi and phi are linearly dependent, or in the language of your vectors, they will all be collinear, they will all be in the same line, or you do not need a different, it is the same, it is linearly dependent. For such linearly dependent situation, the equality will hold, and in general the inequality will be satisfied. So, this is what is called as the Cauchy-Schwarz. So, in principle, you know how to prove this. I want you to redo the same thing in the context of this language notation of the ket and the bra with set of properties which an inner product satisfied, and you should be able to get some results from this. I will be following this notation from the next lectures and so on. So, if you do not know this notation, you will be completely lost. So, please play your hands on writing down what these notations are. For example, if suppose I give you a vector, suppose I give you a state, let us say alpha as 1 times 1 plus I times 2, and I also say that 1 with 1 and 2 with 2. This is just a notation, you can use Greek letters or any arbitrary. So, this is 1, I give 1 with 2 is 0. What is the dual vector to the alpha vector? So, alpha, what is it? So, you can write this as 1 with the coefficient 1, and then 2 with the coefficient I star, which is minus I. Okay. So, when we want to take the inner product of alpha with alpha, you first have to convert the coefficients to complex coefficients, and then we can proceed with this to find the dual vectors. Okay. So this also brings in me a condition of what is linear independence and span of the vector space. Even though I have given it here for some arbitrary vectors in terms of this, what is the span looks like from this vector? There are two vectors which is required to define this alpha. So the span set should definitely include the ket 1 and a ket 2. But an arbitrary beta, if I want to write, if it still involves 1 and 2 for any arbitrary vectors, could be some A times 1 plus B times 2 . This kind of tells me, so alpha and beta, alpha is some specific state, beta is some arbitrary state. Any arbitrary state, I am able to write it in terms of 1 and 2. Linear independence and spanning the space. Since any arbitrary beta is in terms of 1 and 2, it spans the space. And we have also written a condition that 1 and 1, 2 and 1, 2 and 2 is identity, and this one 1 and 2 is, it's 1 and this is 0, not identity, it's a scalar, it's 1. So what is this? What is this condition? It's a basis set is 1 and 2 forms basis set. You all agree? 1 and 2 forms basis set and they are linearly independent. They are in fact orthogonal also. It's orthonormal. These dot product is, these basis dot product is 1. The dot product of these two bases is 0, which is your orthonormal basis. And since it spans, any arbitrary state can be spanned by using these two states, and it is satisfying this property, linear independence and spanning the space. So this 1 and 2 forms the basis set. So what is the dimensionality of the vector space? 2. Dimensionality of the vector space is the number of states in the basis set. So this will define for you a 2-dimensional linear vector space. It could be complex because A and B in principle could be complex coefficients. Is this clear from this example that whenever you have to write the dual vector for any ket, you need to make sure that the coefficients, any scalar multiplying a ket, if I ask you what is a dual vector, if you have a vector psi and I multiply a scalar and call this vector as some phi, what is this one? This one will be A star psi. This A star you can put it this side or that side, it's just a number. Okay. Many of them make this mistake. Mechanically when they write the dual vector, they don't complex conjugate the coefficients. Please remember this. And it plays a very crucial role. Sometimes the observable quantity which you will evaluate will become complex. You don't want that to happen. So when you go to a dual vector space, in real spaces it doesn't make difference. So that's why when you did your 3-dimensional R3, there was no problem. But if you are doing complex vector spaces, which is what happens in all your quantum mechanics problems. So I have taken a simple example of a two-dimensional vector space, and two-dimensional vector space also naturally appear in quantum mechanical systems. Okay. So you have a two-dimensional vector space, and for such cases when I have to find the dual vector, I have to make sure that the coefficients which multiply it has to be complex conjugated, and whichever is the ket, I have to write it as a bra. So formally we will write in an abstract vector space, abstract linear vector space, we will say that we have a set which is a basis set, okay, with the property that phi I, phi j will be delta ij to make it orthonormal basis set. So by basis set, now you should know it spans the whole space and they are linearly independent, and once I say it's orthonormal, then it satisfies this condition. Now I have not said what is the I running from. So I could take values from 1 till n, where n could be arbitrary, need not be 3 or 2 as I was discussing, and n can also run to infinity, can have infinite dimensional vector space. If n is finite, then it is an n-dimensional vector space. Can have infinite dimensional vector space. Here we have taken it to be a discretized index. That could also be a continuum. Okay, so many possibilities are there. So you can have all types of vector spaces, but this property has to be satisfied. And this basis set means any arbitrary state, you will be able to write it in terms of summation over Ci phi I. That is the meaning of saying that it spans the space. You can write any arbitrary state in terms of that. And these two conditions will be sufficient to look at any abstract space. Okay. Okay, so then this brings in for me one small thing which I heard from one of you in the beginning of the lecture, that you have done Gram-Schmidt orthogonalization, right? So let's just go over the Gram-Schmidt orthogonalization in this notation. So this basis states which we have is orthonormal set, but generally you can be given, as I gave you in the beginning, I gave you a simple example which was a non-orthonormal but still a basis set, right? I had an Ex plus Ey, and then Ex plus Ey plus Ez, you could normalize them. This is a basis set in 3-dimensional real space which spans the space, but it is non-orthogonal. And how do you go about finding the orthogonal set? Is by the, so this is not orthogonal basis. How do you find orthogonal basis from the above set? This is your familiar. You first define your first state phi 1 to be equivalent to Ex. And then how do you find phi 2? What do? You take the second state and then subtract out What do you do in, let's take it in this. Okay. You have this state. The first basis I have taken it to be Ex. The second one is making an angle 45 degrees with the first one. But I want to make it orthogonal. How do I do it orthogonal? Take the projection of that vector in this direction, subtract it out, and what you get will be this piece. So let's write this in this notation, phi 2. So suppose I call this to be psi 1, call this to be psi 2, this to be psi 3. Phi 2 will be psi 2 minus projection we have to do. So you will do with phi 1 as psi 2 and take it along phi 1. Will this be normalized? May not be. Whatever is the numerator, I have to take the norm of it to make it to call this like a unit vector, right? So this whatever you find here, divide it by norm of the numerator state. Not writing it, but you understand what I mean, right? Everybody understands? Let's do this for this case. Psi 2 is Ex plus Ey by root 2. You take a dot product with Ex, right? And then this is Ex. Dot product with Ex will give you a 1 over root 2 and then this is Ex. Ex plus Ey by root 2 minus Ex by root 2 will become Ey by root 2. So Ey by root 2, the norm is again 1 over root 2. So what will you get here? Ey, right? So this is what is the Gram-Schmidt orthogonalization written in the Dirac bracket notation. And there is something which you can see here. How do you do phi 3? How do you do phi 3? You need to subtract the component along phi 1, component along phi 2 and then the normalize that numerator and that will give you the phi 3. So let's write it. So take phi 3 to be psi 3 minus phi 1 with psi 3 phi 1 minus phi 2 with psi 3 phi 2 and then you have to whatever is this numerator that has to be taken the norm. So that will give you the, so and this will turn out to be in your specific example as Ez. So we could do this Gram-Schmidt orthogonalization to find all the 3 basis vectors neatly. Okay. So we will continue from here in the next lecture. Slowly introduce operators, linear operators and so on, and then we will see how to elegantly follow this notation.